Okay, by the end of last lecture, we have proved the Radon-Nikodym theorem for the case where nu and mu are both positive and they're defined on, or they're finite measures. Okay, to extend this to the most general case, we first consider the case that both of these two measures are sigma finite, meaning that x can be decomposed into a countable union of sets, then such that on each of these sets, the nu and the mu are finite. Okay, so to this end, let's consider the decomposition of x into either this form or this form. So this decomposition, we can always assume that these AKs are disjoint, because otherwise we can just for each AK, we can just define to be the difference of this set from the existing ones. So for example, if you do have some AK, the union of AK that is equal to X, we can always define AK, the new AK, let's say AK prime, to be the difference of these two, where J is from 1 to K minus 1 AJ. Right, so in this case, these sets will not overlap. Okay, so we can decompose it into such set, and the mu will be finite on each of this, and similarly, the nu will be finite on each of this. Okay, so there are disjoint unions and disjoint unions of x, and on each of these, we know that the mu and nu are finite. And then we can consider the such kind of intersections. So we pick up any one of this, and any one of this, we take the intersection. We will get, again, countably many sets. And these sets will not overlap either, right? Because these are disjoint. So this will be disjoint as well. Then we re-denote these sets as CK. Then we can show that this CK is again a disjoint union of X, and also the two measures mu and nu are finite on each of these sets. Okay, so they are all finite on each of these sets, and then we can use the result just proved on each of these sets. We can find this lambda k and fk. So these are specific to this set only, and it's 0. They are both 0 outside of the CK. We can know that these two will satisfy the Radon-Nikodym theorem we just proved. The mu can be written in the sign measure mu. In this case, we are assuming the mu is positive as well, but the mu can be written as a decomposition into this form, which is decomposed into lambda k and rho k, but the rho k part can be written as it's just the fk times the mu. Okay, so the rho k is just related to the measure mu in this way. Now that's what happens on each of the sets ck. So if we consider the entire x, we just notice that this ck form a disjoint union of x. So for each ck, we have this lambda k, fk, and we just need to take the sum of them. And take the sum, then we'll have this lambda defined on the entire x, since each of this is defined on the ck. And similarly, we can define f to be the sum of these fk's, where each of these fk's is defined over ck. And then it's easy to show that the nu can be decomposed in this way. Okay, can be decomposed into this way. So this lambda, as just we said here, the lambda k is a orthogonal complement of the mu, and this part is absolutely continuous with respect to mu. Okay, and then we'll also inherit that same property for this final form. Okay, and up to this point, we show that if mu and nu are both sigma finite positive measures, the Radon-Nikodym theorem still holds. And the most general case is that the nu is sigma finite signed measure rather than just a positive measure. And we know that for a signed measure, we can decompose it into the two positive measures, mu plus and mu minus. So the nu will be just equal to nu plus minus nu minus, right? That's the decomposition theorem we discussed before. So for each of these two measures, then these are both positive measures, and then we can apply the result we just proved. And for each of them, we can find the lambda prime, the f prime, the lambda minus, and the f minus, so that we can decompose each of these two sets into this form. Okay? And again, these are the Radon-Nikodym decomposition. As we said, this will be this is the part that is orthogonal complement of this nu, and this part is absolutely continuous with respect to mu. Okay, similarly for this one, and then we just need to take the difference of these two, we'll get this final decomposition. So you can see that this will be pretty much straightforward as long as we can prove the Radon-Nikodym theorem for the finite positive measure case. Okay, so this completes the whole proof. That shows the general result we described in the Radon-Nikodym theorem. Okay, now, so just to remind the decomposition we obtained by the Radon-Nikodym theorem, the decomposition we said is called has a name in the history. It's called the Labega decomposition. So let d nu equals to d lambda plus f d mu be the decomposition in the Radon theorem this decomposition is called the Labega decomposition of mu of lambda with respect to mu. Sorry, of mu with respect to mu. Okay. So this for any given finite sigma finite sign measure nu and a positive measure sigma finite positive measure mu, we know that by Radon-Nikodym theorem we can decompose this nu into this form, where this part is a orthogonal completion of mu, and this part is absolutely continuous with respect to mu, and this is called a Labega decomposition of mu with respect to mu. And in addition, f is called the Radon-Nikodym derivative of nu with respect to mu. Okay, so f is also denoted by d nu d mu. Okay, so when you see the Radon-Nikodym derivative, that means the function that we use to define the absolutely continuous part of the signed measure nu with respect to the positive measure mu. Okay, that's the Radon-Nikodym derivative. Okay, lastly, we give a result about this Rodin-Nikodym derivative. It follows the common rules we had for the standard derivatives in calculus. The key thing is the two key things are the change of variable and also the chain rule, which hold in this case as well. Okay, suppose nu is a sigma finite signed measure. And these two are sigma finite measure. Okay, this lambda is not the decomposition of nu. Okay, it's just another signed measure where this nu is absolutely continuous with respect to mu, and the mu, on the other hand, is absolutely continuous with respect to lambda. Then the following statement holds. The first one is the chain rule. Sorry, the first one is called the change of variable. What it says is that if a function g is nu integrable, okay, it's nu integrable, meaning that g is mu measurable, and also the integral of g with respect to the measure nu is finite. Okay, then this is mu integrable. Here the d nu and d mu is the Rodin-Nikodym derivative we just defined. Okay, will be actually the function f we got by the Labega decomposition of the signed measure nu with respect to the positive measure mu. Okay, so this g times the d Rodin derivative is mu integrable, and the integral of g with respect to the measure mu is equal to the integral of g d mu d mu d mu. Okay, so this is we expand this after we finish the second statement. The second statement is the chain rule. And what it says is the Rodin-Nikodym derivative of nu with respect to mu is equal to the Rodin-Nikodym derivative of mu with respect to, sorry, it should be lambda with respect to mu times the Rodin-Nikodym derivative of mu with respect to lambda. Okay, and this is lambda almost everywhere. So both of them you should treat as functions, lambda measurable functions, and what we are trying to show here is that they are equal almost everywhere in lambda. I would say in lambda. Okay, so this is the chain rule and the change of variable. Okay, let's give a proof for this. So first, let me finish the explanation for the change of variable. So this will be for any new interval function g. This is the only function g, but this is the Rodin-Nikodym derivative, right? So we treat this as a whole. This is a mu integral function, and also we take the integral of this one with respect to the mu. We show that this is just the same as taking the integral of this with respect to the nu. That's the change of variable. It's basically you change the variable. You're originally using the variable, for example, x and using the new x as the measure. Now you can use mu as the measure. But the difference is that you introduce this this Radon-Nicolin derivative here. Okay, so that's the changeover variable. Okay, so to prove the first one, we can first show that this equation holds. This equation holds for the G for characteristic functions of a measurable set. Okay, and if we can show that, then because of linearity, we can show this for simple functions, for G to be single functions, and then we can approximate any measurable function using the sequence of simple functions. Then we can show this for general functions. So essentially, we just need to show that this is true for G to be a characteristic function of a mu measurable set. Okay, so let G to be a characteristic function of a set E, which is measurable. Then we can show that on the one hand, we know that the nu of E is equal to the integral of G times d nu, right? Because this G is just a characteristic function of E. Okay, and on the other hand, we can show that the integral of G d nu d mu, this is equal to E because G is a characteristic function. So this is just that. Okay, and remember what this one is. This can be treated as this is equal to the f, such that the nu can be written as f times d mu, right? This is equal to the f there. Okay, and that also means that this is just equal to that, and these two, both of these two are equal to the measure of E, the mu of E. So that means these two are equal. Okay, hence this G is equal to the G d nu d mu. Okay, and now, as we said, the E is arbitrary, and then we can show this is true for arbitrary characteristic function of E, and then we use the linearity, then we use the approximation of general measurable function using a sequence of simple functions. We can prove this one. Okay, so that's the proof for the part one, pretty easy. The second part for the chain rule. So for the chain rule, we need to show that this function, this Radon-Nicolin derivative, these two are equal. Okay, and to show this, let's again show that for any, again, let this G to be, let some function G to be E, then we can see that the integral of G d so on the one hand, I know that this d mu is equal to mu of E, right? This is the one thing that we know. And on the other hand, we know this, according to the chain rule, we know this is equal to the G times d mu times d mu. Okay, we know that, and that's equal to this. And then we also know that when we set this G, we can set this thing together as G. Treat this whole thing as G. And then using the changeover variable, the item 1, this is also equal to the G d nu d mu. This whole thing is the G as before, and then this d mu d lambda. Okay, so this is true for any set E. So that's why, since this is true for any E, we know that the okay, and on the other hand, we know, by the way, on the other hand, we know this is equal to, again, we know that's equal to that, and it is also according to the chain rule above. This is equal to G d nu d lambda. So this is the Radon-Nicotinne derivative of nu with respect to the lambda. So that shows that these two must be equal, and that's why, since these two are equal for any G, and this G can always just the Cassé E, and this part is also the Cassé E. So we know that these two d nu d lambda is equal to d nu d mu and the d mu d lambda almost everywhere in lambda, because for any measurable set E, these two integrals are the same. Okay, so that means these two are actually the same. Okay, so that finished this subsection. Next, we're going to talk about the differentiations. So this is a very old topic in calculus, but since we are studying the Labega Theorem in this course, we want to see what happens when we consider all the integrals in the Labega sense. And do we have the one of the most important results I'm going to show later is that if the fundamental theorem of calculus still hold here, since the integral is defined in the Labega sense, and the differentiation and everything like that should be carefully rechecked. Okay, so differentiations. Okay, we'll only give the main result in this section because the major theory is in the next two sections. For this section, we consider functions defined on R only because we're talking about differentiation. So we'll focus on the 1D case. For high D case, it's easy since when we talk about the high dimensional functions, the derivative means the gradient, and we need to take partial derivatives on each of those coordinates. So everything boils down to just the 1D case. So in this subsection, we only consider the 1D case. So the first definition is called the Vitali cover. Actually, this one has some other usage, but the main purpose for this Vitali cover here is to prove the Labega theorem. But this is the Labega theorem is a pretty long one, and we're going to skip that proof itself, but we're going to just give the result. And this Vitali cover is useful in the proof for this purpose right here. So I still just give you the definition for a reference. The Vitali cover. So now, as I said, I only consider R only. Okay, the Vitali cover is that a collection of closed intervals. So the closed interval, the collection F of closed intervals on this R is called a Vitali cover of the set E if for any epsilon and any x in E there exists a set or closed interval from F such that X belongs to I and the measure of I is less than epsilon. Okay, so that means for every point in E, for any for however small epsilon you want, we can find some interval, closed interval, such that the length of this closed interval is smaller than epsilon, and it covers the point X. X is a point in the I. Okay, so let me give you an example. Suppose the E is the closed interval AB in this RK. It's a collection of countably many points, which are the rational numbers in the interval. And the IKM is the closed interval centered at RK with the radius 1 over m. Okay, and then you can see that F is a Vitali cover of E, where this K is from N, and also this M is from N. Okay, and the reason for this is because for any, so this F is just all the intervals of this form. This is the rational number, and its radius is 1 over m. So for any rational number from E, apparently they can be covered by this, right? And it doesn't matter how small you want your epsilon to be. We can choose m large enough so that this one has a length less than epsilon, and we can cover that rational number. But also for irrational number, we know that the rational numbers are dense in the interval. So for any irrational number, we can find some. For any irrational number and for any epsilon, we can find for any irrational number. Let's say this is a Q. And for any epsilon, we can find this interval small enough so that the interval centered at RK that is sufficiently close to Q with the radius sufficiently small, we can cover this Q, but the radius is still less than the prescribed epsilon. Okay, so that's a pretty straightforward example. Now the lemma of the Vitali covering lemma is that covering lemma. So the Vitali cover tells us that we can use arbitrarily refined closed interval to cover a point, any point in the set E. So the Vitali covering lemma is to say that suppose we have a set E that has a finite matter, and then we can find a finite many covers from this family F such that they can almost cover the entire E. Okay, in the sense that for any epsilon, we can find a finite collection or finite number of intervals from the family F from the Vitali cover such that these covers are disjoint, or these sets are disjoint, but they're the E minus the union of these disjoint intervals has a measure less than epsilon. Okay, so that's the Vitali covering theorem lemma. So specifically, suppose that E is a subset of R, and we don't even need this E to be measurable. It's just say the outer measure of E is finite. If F is a Vitali cover of E, then for any epsilon greater than 0, there exists a finite disjoint sets. Let's say this I at 1 through ik. They're from this family. They're disjoint as well, such that the outer measure of E minus the union of Ej is less than epsilon. Okay, so for any epsilon, we can find such a finite disjoint collection of sets from this family, such that the union of them almost fill up the E. The difference of these two has an outer measure less than epsilon. Okay, so this is solely used for the proof of the Labega theorem later on, but doesn't have other uses, so we'll skip the proof here. But the proof is given in the notes. Okay. And apparently we can extend this Vitali cover to the n-dimensional Euclidean space, and even for the case where E is not finite. But if E is not finite, we can just we know that the entire R is a sigma finite set, so we can partition that into a countable many sets. For example, from k to k plus 1, that's one interval, and over this interval we can find a collection of finite points such that finite sets such that they can fill up this E, almost fill up this E, and then we can do this for each of those partitions. Okay, and also since we allow this k to be in this case we only use to find many of them, but imagine that if you have this as epsilon k where k goes to 0, then we can find a countable collection of this disjoint sets, not just from 1 to k, but 1 to infinity, countable many of them from this collection, such that the outer measure of this E minus the countable union of them is equal to 0. Okay, so that's pretty easy to show. Okay, now since we were talking about the derivative, let's recall what's the derivative. If we follow the original definition for derivatives, we actually have left the derivatives and right derivatives. If you have seen this in analysis, and for the left or right derivatives, we can it doesn't matter if they exist. At least the supremum or infimum of each side exists, and these derivatives are called Dini derivatives. Dini derivatives. So what are these? Suppose we have a function f from R to R, and define. So there are 4 derivatives we're going to define. The first one is we use the notation d plus f. So this is defined as the plus means that it's a derivative on the right of the point x. On the right of the point x, so it's lim sup. If it's on the top, it's superscript of d is on the top, which is defined as f of x plus h minus f of x divided by h, where h is going to 0 from positive. Okay, and similarly the d plus here is a lower limit h minus f of x divided by h. And you know that if these two limits are equal, that means if the upper limit is equal to the lower limit, that just means that the limit exists and these two are equal. They're called the limit. Okay, so if d plus f x equals to d this plus fx, then the limit of f of x plus h minus f of x over h goes to 0 exists. And this value is equal to the common value of these two. Okay, and in this case, we say the function f is right differentiable. Okay, right differentiable at the point x. And similarly, we can define this d minus f, and this is the left. When we see minus is left, is the upper limit for f of x minus f of x minus h divided by h. And similarly, d minus f here is the infimum, lower limit, sorry, the lower limit of f of x minus f of x minus h divided by h. So again, for these two, if these two are equal, then we know that the limit of this exists, and that this value is called the left derivative of the function f at the point x. Okay, and if both of this, so this is called the upper right Dini's derivative. And similarly, the second one is the lower right, and then the upper left and the lower left. Okay, and there are four derivatives, and they are always defined. Doesn't matter if function is differentiable or not. They're always defined. And as we said, if these two are equal, then we say that the right derivative exists. If these two are equal, then we say the left derivative exists. And if the left derivative, right derivative both exist, and they're equal, then we say the function f is differentiable at the point x. Okay. Okay, so this is what we know. But in general, what we this four may not be equal. And in that case, at least what we know is that just a few remarks here. At least what we know is that the first is this is upper limit, this is lower limit. That means this, at least this is greater than that. Okay, this is always greater than that. And similarly, this must be greater than or equal to that. So that's one of the remarks I want to make. The second is that when we consider, for example, we consider negative f. So the first one is that the d plus f, like this, is less than or equal to this. And the d minus f is less than or equal to this. Okay, so that's one. The second one is that if you flip the sign of f, so you consider negative f impact of f, then the lim sup becomes the lim inf of negative f, right? Lim sup of positive f is equal to the lim inf of negative f. So that's why it's easy to check that the upper right limit, upper right derivative of negative f is equal to negative of the lower right derivative of f. Okay, this is because this one on the left is the lim sup of negative f x plus h minus negative f of x, h goes to 0. Okay, and apparently we can remove the negative, put the negative outside, then just negative of lim inf, h goes to 0, or this f of x plus h minus f of x divided by h. And on the right hand side, this is just equal to that. Okay, and similarly, we can show that this is equal to negative of this. Okay, and again, this, as I said, in which case, in this, if these two are equal, then the right derivative exists, and these two are equal, then the left derivative exists, and if the four are all equal, then we say the function is differentiable. Okay, so let's look at the example. Suppose we have four numbers. A is less than b, a prime is less than b prime, and let's define the function f of x to be, so it's separated to three cases. If x is bigger than 0, then this is the sine, ax sine of this plus the bx cosine of that. That's for the case where x is greater than 0. And if x is equal to 0, then it's just 0. If x is less than 0, it's the same as thing as that, but we are just using a prime b prime instead of ab. Okay, and for this one, you can check the four Dini's derivatives. And for example, we can check the upper left derivative, Dini derivative, at the point 0. Okay, if it's not 0, apparently the function is differentiable. So we know that the four derivatives exist, and we can actually take the derivative, as we know, you learn from calculus. But right now, if it's at 0, let's see what happens. If it's at 0, then according to the definition, this should be the lim sup of h going to 0, where this is f of h minus f of 0 divided by h, right? And f0 is 0, so this part is just 0. And f of h is, we just need to plug in the value of h. And that would be ah sine square of 1 over h plus bh cosine square 1 over h divided by h. So that means this is equal to the lim sup. And we can cancel the h on the numerator denominator. We have a times sine square 1 over h plus b times cosine square 1 over h. Okay, so as you can see, when h goes to 0, this will oscillate. This will oscillate between 0 and 1. This will also oscillate between 0 and 1 because of the square here. Okay, between 0 and 1. So since a is less than b, we can always choose we always find a sequence of h is positive, then go to 0, such that this one is equal to 1. Okay, and this is equal to 1 means that this is equal to 0. So in that case, it can take the value of b. So the lim sup of this will be equal to b. Okay, so similarly, you can see that the lower right Dini derivative will be equal to a. Okay, this actually at 0 is equal to a, and you can also show the other side. It's pretty easy to show. You can check it yourself. Okay, and next example we're going to give is that if the function f is continuous over the interval ab, then there exists a point in AB and K in R. K is some number. We're going to specify what that number is, such that the lower left Dini derivative at x0 is bigger than or equal to K, and bigger than or equal to the upper right of the derivative, either this or that. So equal to K less than equal to D plus f of x0. Okay, so we can find, at least we can find some x naught and k such that either this hold or this hold. Okay. To prove, the proof is by observing this. We set this k to be f of b minus f of a divided by b minus a. Okay, so roughly what this means is, say we have this as a, b, and we have say some function like that, and then this is the f of a, f of b, right? Then we make a connection of these two. Then this k is just the slope of this secant line, right? And then you can define the gx to be f of x minus kx, k times x. So k times x. K is just a number now. Okay, and then it's easy to check that g of a is equal to g of b. Okay, you can check g of a is equal to f of a minus b is just k is just that times a. Okay, and similarly the g of b is f of b minus f of a, b minus a times b. Okay, we can check that these two are equal because the numerator is just fa times b minus a minus fb a plus fa a divided by the b minus a, and that is equal to, as you can see that fa times a is cancelled, so we will have f of a times b minus fb of a divided by b over a, and that you can easily show that it's also equal to this. Okay, it's easy to show that it's equal to that as well. Okay, so that means taking out this of this kx, the gx will take the same value at the a and b. Okay, and since the f is continuous and the kx is also continuous, so we know the g is also continuous. And it's continuous on the closed interval means that it can achieve maximum or minimum somewhere. So then g achieves max or min at some point x naught. Okay, let's say that it achieves the maximum at x naught. It achieves maximum at x naught means that, say this b, say the g takes the value like this. So what we know about it is that this is the level. Okay, it could be like this, or it could be like that, or like this. So it must attain maximum or minimum somewhere. That's the function g. So suppose it attains maximum, say it attains maximum here at x0. Then since it's the maximum, we know that the upper limit of gx plus h minus gx over h, the upper limit of this will be g0, if h goes to positive, must be less than or equal to 0. The reason is that this must be bigger than or equal to this, since this is the maximum value. This value is the maximum value. Okay, and this which actually the d plus g at x naught. Okay, and similarly we can show that d minus g x naught, this is equal to the lim inf h goes to 0 gx0 minus gx0 minus h over h. So this must be greater than or equal to 0. Okay, because again doesn't matter what this one is, it must be less than or equal to this value. Okay, so it's always greater than or equal to 0. And now we show that the d plus gx0, this is just the d plus, because g is defined as f minus kx, and this is differentiable, so it's always so fine. It's always okay. The Dini's derivative is just equal to the derivative of this term itself, which is equal to k. So this is just that, right? Just f minus k is less than or equal to 0. And on the other hand, the second one we have above means that d minus f equals 0 minus k will be greater than or equal to 0. And these two together implies that the d plus f of x0 less than or equal to k, and it is less than or equal to d minus f of x0. Okay, this is the case where the x0 is a maximum. And if it's minimum, we'll get the other one. Okay, so what we showed is this one, but if it's the minimum, then we'll get this one. Okay, so that's the proof of this. And next, we're going to give the result of the Labega theorem. It's pretty simple theorem. It says that if we have a function f defined over the interval ab to a real number, is non-decreasing. Then, as long as it's monotone, it's non-decreasing, but it can be also non-increasing. We just consider this non-decreasing case without loss of generality. So then f, as long as f is non-decreasing, then f is differentiable almost everywhere. That is differentiable means that for almost every x over this interval, the four Dini's derivatives are equal. And not only that, the integral of the derivative, this derivative exists almost everywhere, so we can define this function. For the differentiable point, it's just a derivative. It's not differentiable, non-differentiable point, we can take an arbitrary value. But taking the integral of that doesn't change the value, since this is differentiable almost everywhere, only non-differentiable at the measure 0 set. Okay, and this is less than or equal to f of b minus f of a. Okay, so as long as non-decreasing, the function is differentiable, but we don't have the perfect result that we wanted. The integral of the derivative, which is always well defined as we said. You change the value on the at the non-differentiable point. We set to any arbitrary value at those points. It doesn't change the integral here, but this integral can only be shown to be less than or equal to fb minus f of a. Okay, so it is indeed greater than or equal to 0. That's not difficult to show, but it's not. We don't have this equal to that in general. Okay, so that's the Labega's theorem. As I mentioned earlier, we're going to skip the proof, but the proof is a little bit long, but it's shown in the notes. So if you're interested, you can take a look. But we just look at the consequence of this. Why we only have this is less than or equal to? We only have this is less than or equal to. This is because the function is not good enough, so for this to be equal. Okay, we will talk about the necessary the sufficient condition for this to be equal, or in other words, the fundamental theorem of calculus exists in the Labega sense. We show that later, but if it's just non-decreasing, that's not sufficient. Okay, so we can take an example. It's a pretty simple example why this may not be equal. For example, this f of x is defined over from 0, 1 to r. Okay, and it takes the value, say 0 when x is between 0 and 1/2, and takes value 1 when x is between 1/2 and 1. Then, this function is pretty simple. It just looks like this. from 0 to 1/2, it takes the value here. It doesn't take the value here, but then that the value 1, it's going up like this. Okay, the scale are different for the x and y, but you know the idea. Okay, so it goes up like this. So you can see the function is differentiable almost everywhere, right? It's only non-differentiable at this point 1/2. So it's differentiable almost everywhere, and the derivative is equal to 0 when it's differentiable. Okay, so the f prime is equal to 0 for all the x not equal to 1/2. Okay, but you take the integral. If this function f prime is 0 almost everywhere, it's just not defined, or it can be arbitrary value at point x equal to 1/2. Then the integral of that right now it's just 0 to 1. Of that, apparently since it's 0 almost everywhere, so it's just a 0. But on the other hand, f1 minus f0 is equal to 1. So these two are not equal. Okay, so but this is less than that. Okay, so we can show this less than equal to that, but it's not equal. Okay, another theorem we're going to give is about infinite sum, or the derivative of infinite sum. Suppose we have a sequence of functions defined over the interval, and each of them is non-decreasing. Suppose this is a non-decreasing function. For every k. So every k is a non-decreasing function in x. And the sum of fkx for each point x, this series x converges. For every x in the interval AB. Then we can show that the sum of this, we can define this to be a function as a series for each point of this function. It takes the value of this limit of this series. And if this is the function, so let's say this is called the f of x. Okay, for each point x, it's just the f of x defined as that value. The derivative of this is equal to the derivative on each one of them and take the sum. So we can exchange the derivative and this infinite sum. And this holds for almost everywhere on the interval. Okay, let's see how to prove this. Since this fk is non-decreasing in x, we know that according to the Labega Theorem above, if the function is non-decreasing, we know this function is differentiable almost everywhere, and also know the derivative is bounded by fk of b minus fk of a. Okay, so but at least we know that this k prime exists almost everywhere, and also the derivative must be greater than or equal to 0, apparently since the function is non-decreasing, so it must be greater than or equal to 0 almost everywhere on this interval AB for any k. Okay, so we know that, and then we denote this sk to be the partial sum of the fk. So it's the fj for j from 1 to k. And then the remainder we call this rk, which is the sum of the others, k plus 1 to positive infinity of fj. Okay, then apparently the f we had earlier, the f of x is just equal to sk plus rk, skx plus rkx. Okay, so we know that. But on the other hand, what we want to show is that the derivative by the way, since fk's are all non-negative, are all non-decreasing, so this is not each of them is non-decreasing. So take the sum, it's still non-decreasing. So sk is non-decreasing in x. Okay, and also the rk is non-decreasing in x as well. And according to the Labega theorem above, both of them are differentiable almost everywhere. Okay, and both of them are actually greater than, the derivative of each of them is greater than or equal to 0 almost everywhere as well. So now, sk and the rk are both non-decreasing in x. We know sk prime, rk prime, they're both greater than or equal to 0 almost everywhere, and they exist almost and also non-negative almost everywhere. So we have we consider f prime. This is supposed to be sk plus rk prime. Okay, since f is also non-decreasing in x, so the derivative exists, and also it's just equal to the derivative of this, and then we know that's just equal to sk dart prime plus rk prime. So this exists almost everywhere, so we don't need to worry about that by taking the derivative inside. And now, what we need to show is that this one, since sk is a finite sum, so the derivative of sk is just equal to the derivative of fj for j, this, and then we have our k prime. So this part is equal to, because we have finite sum, so taking the derivative, it's just taking the derivative in the inside due to the linearity of derivatives. So we know that. And then we still have this rk prime. And now the only thing we need to show is that when k goes to infinity, this one can go to 0 as k goes to infinity, right? Because this first term will be the right-hand side we need, will be this part I need. But the right-hand side, the rk prime, I need to show that it is going to 0 almost everywhere. Okay, now we need to show that the rk prime goes to 0 almost everywhere. Okay, and to show that, first notice that rk prime is equal to again the sum of fj, j from 1 to k, j from k plus 1 to positive infinity prime, and they can be written as fk plus 1 plus the sum of rk plus 1, right, prime. And now we know that both of these two functions are differentiable almost everywhere since they are non-decreasing in x. So I know that it's just fk plus 1 prime plus rk plus 1 prime. But we know that the f prime is greater than or equal to 0 since f is non-decreasing. We know that it's greater than or equal to rk plus 1 prime almost everywhere. And now I know that for almost every x, this rk prime of x is decreasing in k. So for almost every x, the rk prime of x is decreasing in k. Right? It's decreasing in k. So let's say that this is decreasing, and we know that every one of them is greater than or equal to 0. That means so we know that this is a decreasing sequence of numbers at point x. For each point x, for almost every x, this is a decreasing sequence, decreasing numerical sequence in this bounded below by 0. So we know that the limit exists. So let's say that the limit is called phi. Let phi of x to be the limit of rk prime x when k going to positive infinity. And this phi x is defined almost everywhere. And if it's not defined, or this r prime is not defined, or it is not converging at the point x, and then we just set the phi x to be arbitrary value. But the point right now is that we know this is greater than or equal to 0, since every one of our k prime is greater than or equal to 0. On the other hand, we know that the integral of phi, while each is non-negative, so the integral of that must be greater than or equal to 0 as well, right? And also, this is just equal to the integral of the r prime, the limit of r k prime dx. Now we have the limit inside. We can use the Vitali's lemma. This is less than or equal to the limit lim_inf, or lower limit of the integral of this rk prime x dx. Now for each of these integrals, we know this is equal to, or is less than or equal to the rk b minus rk a, right? Because we know that this is less than or equal to this. Okay, so it's that. But we know that the series converges. Remember that rk of x is defined to be the sum of fj of x, where j is from k plus 1 to infinity. And they converge. That means when k goes to infinity, this goes to 0 as k goes, right? As k goes to infinity. So that means this goes to 0, and this also goes to 0. So this is actually equal to 0. Now we show that we have the non-negative measurable function phi, and the integral is equal to 0, means that phi is equal to 0 almost everywhere. Okay? So phi is equal to 0 almost everywhere. Okay, and that shows that the rk prime at x goes down to 0 as k goes to infinity almost everywhere. Okay, and this completes the proof, since we know that this one goes to 0 almost everywhere. So that's why this just will converge to that as k goes to infinity. Okay, now let's look at the example. This example is pretty interesting. What it says that we can find a strictly increasing function. We can find a strictly increasing function, but the derivative exists as 0 almost everywhere. Okay, and this is quite different from calculus. We know that when the function is strictly increasing, then it's likely that the derivative should be positive, at least positive somewhere, right? But we can find some function that is strictly increasing, but the derivative is almost everywhere, 0. Okay, 0 almost everywhere. So for this example, let's consider the set of rational numbers in 0, 1. Okay, so let's say this is a set of rational numbers in between 0 and 1. Then we define, since we enumerated this rk, we define this fk to be a step function. It is 0 when the x is less than rk, and when it is bigger than rk, we set it to the value 1 over 2 to the k. Okay, it's a pretty small number, but at least it's positive. Now we let Sx to be the sum of fkx, k from 1 to positive infinity. Then we know that for each of these fk's, it is non-decreasing, right? It's non-decreasing, and this is a sum according to the example above. the theorem above, we know that the derivative of this exists and is just equal to the derivative, the sum of the derivatives, right? But look at the right hand side right now. The sum of derivatives, they are each of this, the derivative is 0 except at one point, right? Because of the way we define the fk. So for each k, the fk is differentiable, is only not differentiable at one single point rk, and other than that point, the derivative exists and is 0 at those points, right? Because it's piecewise constant. So it just does not exist at rk, but otherwise the derivative is equal to 0. So that means this is equal to 0 except at one point. Okay, and then take the sum, we'll have a function that it is 0 almost everywhere. So the s prime is 0 almost everywhere in the interval 0 to 1. Okay, but on the other hand, we can easily show that s is strictly increasing. Because for any x less than y in the interval 0 to 1, there exists some rk in between. There exists some rational number in between, so that the sk, this sx, just continue writing that, s of x must be less than s of y. Right? The reason is, at the point of y, we have at least increased by 1 over r to the k for rk between let's know that's less than or equal to s of x plus rk. It should be less than that, right? And this is less than or equal to s of y, where this x, there's a rk in between x and y. Okay, so that means this is strictly greater than the sx. So s is strictly increasing, but the derivative exists and is equal to 0 almost everywhere. Okay, so that's a interesting example.